Welcome back, statistics scholars. Our last video for the second exam is going to be more on null hypothesis significance testing. But these are going to be sort of the fine details today. Some sort of basic definitions, some conceptual, theoretical definitions that you have to know as a part of a well-rounded education in statistics. What we're going to talk about today aren't going to be sort of the nuts and bolts practical things that we sort of learned about last time, the times before that, that will allow us to ask and answer research questions. Rather, these are more conceptual, theoretical, but again, still important from a theoretical standpoint. And so essentially today, we're going to be talking about what happens after you make a decision. After you have conducted a null hypothesis significance test, are there other considerations you need to have? And the answer is yes. Once you've made your decision about your research question, either rejected the null and happy because that's what you want to do, you've concluded that the groups are different, that your one sample is statistically significantly different from the null hypothesis comparison population, right? You've either done that, rejected the null, which is what you want as the researcher, or you've failed to reject the null. You've retained the null. And you're bummed out because then you're saying that the groups are not different, that there is no effect of your sample. Your sample is not different from that known population. Either way, there are some other theoretical considerations that we have now. And that's what today's lecture is going to be all about, learning these sort of fine detail theoretical ideas. But before we launch into that, I want to go over that example, one of the examples that we went over last time, just to make sure we're all on the same page and we all remember our discussion of what null hypothesis significance testing is. And so here is my research example. Do pre-law students score higher on the ACT than students in general? So I know that I'm trying to see if pre-law students are different than the general population of students sort of in general. So I've got these two groups, pre-law students and then students in general, and I'm curious if there's a difference in the averages for the ACT for these two groups. That's the idea. And I'm really specific where I say higher. So I know this is going to be a directional hypothesis because I've made it clear that I'm only interested as the researcher in determining if these pre-law students have higher ACT scores. And so here are if we look over here, here is that null hypothesis, which is the opposite of what I think is going on. And here's that awesome alternative research hypothesis, which is what I actually think is happening, or what I'm hoping to find support for as the researcher. So let's start with the alternative. H sub 1 is my formal symbol. That means the alternative hypothesis. H sub 1 is that the average mu in the population for law students is greater than 21. So that's what I'm hoping my sample will establish support for. I'm hoping my sample will support this idea that the average ACT score for law students in the population, because notice there's a mu there, I'm always trying to make decisions about populations, is greater than 21. My research hypothesis is that the average ACT score for law students is greater than 21. And so my collectively exhaustive, mutually exclusive opposite is this null hypothesis. This null hypothesis is H sub 0, that's the symbol that stands for the null hypothesis. That null hypothesis says that the average for law students, right here, is going to be less than or equal to 21. And then less than and equal to is being treated as the same outcome, right? Just not greater than. In fact, less than or equal to, just not greater than. That's sort of the null hypothesis that I'm hoping as the researcher to reject. And so then I gather my one sample of 9 pre-law students, and then when they get an actual sample average of 23, where then I'm going to then compare that to the null hypothesis population that has an average of 21 and a standard deviation of 6. And 23 is technically not the same as 21, but these 9 students, they could just randomly have a higher average of 23 because samples are going to be different from each other. If I theoretically grab an infinite number of samples from the population, sometimes I'm going to get sample averages like 23 just due to chance. And so I had to decide which this is. Is the null hypothesis accurate? 23 is just a little bit higher than 21 simply due to sampling error, simply due to chance because samples are going to be different sometimes, right? Or is 23 higher than 21 because there's something meaningfully different about these pre-law students? And that becomes my alternative research hypothesis, that these pre-law students, these 9 pre-law students, are in fact higher because of something meaningfully different about them. And so in order to address these two possibilities, I'm going to create my sampling distribution of the mean where I assume the null is true. I create a null hypothesis sampling distribution of the mean. And here is me doing just that. So here I have it, right? I've calculated standard error. Let's go back to this example here. I'm now going to create my null hypothesis sampling distribution of the mean, which is my theoretical, hypothetical, probability density plot of an infinite number of sample averages where I assume the null is true, that these 9 students are simply a random sample from the population that also has an average of 21, because the null hypothesis says that these law students aren't any different than the general population. So I create a theoretical, hypothetical, infinite number of samples distribution of an infinite number of sample averages where I assume the null is true, where these law students also have an average of 21. And so let me actually draw it for you, and then I'll show you the pretty picture. All right, so if I take the numbers from here, in order to create my null hypothesis sampling distribution, according to the central limit theorem, an infinite number of averages will be normally distributed. So that's great. I get to draw something that's normally distributed. So according to the central limit theorem, an infinite number of averages will have this pretty bell-shaped curve, right? Also, according to the central limit theorem, the average of all the averages will be equal to the population average. Well, this is the null hypothesis sampling distribution. And the null hypothesis said that the average would be 21. So I'm going to center this infinite number of sample averages on 21. But now I have to calculate standard error. Well, here it says that the standard deviation in the population, the null hypothesis comparison population, is 6. And so to calculate standard error, it's sigma over the square root of n. So sigma is 6. And how many people are going to be in each of my infinite number of averages? Well, my one sample has 9 people in it. So I guess my infinite number of averages will also have 9 people in them. So standard error is 6 over the square root of 9. That's 6 over 3. So standard error in this example is 2, right? So 21 is here. And then 1 standard error away is 23. 2 standard errors away is 25. 1 standard error below would be 19. And 2 standard errors below would be 17. And so this is my null hypothesis sampling distribution of the mean. This is first assuming that the null hypothesis is true, that any sample of lawyers I grab are going to be exactly the same as the general population, and so also will have an average of 21. And a standard deviation of 6, that they're exactly the same as the general population. And since I know I'm going to grab one sample of 9 students, 9 pre-law students, my infinite number of sample averages will also each have 9 students in it. So this distribution that I've drawn here is the theoretical, hypothetical, infinite number of averages for an infinite number of pre-law students, where I've grabbed samples of 9. I grabbed 9 pre-law students, calculate their average, toss them back. Grabbed another 9 students, calculate their average, and toss them back. And if I assume that the null is true, then these law students are also going to have averages centered on 21. And so now I've got my theoretical, hypothetical sampling distribution of the mean where the null is true. And now I'm going to use this as a tool, right, to determine where my actual sample data ended up on this null hypothesis sampling distribution of the mean, right? But first I have to come up with a rule. So here's that same graph drawn all pretty, right? I've got the null hypothesis saying that the average will be 21, right? So here this one is also centered on 21. My standard error is 2. So 21 plus 2, 23, plus another 2 is 25, right? Plus another 2 would be 27. Because this is a directional test, I'm going to put all of my area of rejection in one tail. This is a one-tail test. And so what I'm going to say, my rule, my alpha, is my area of rejection is any average in here, in this red area here, I'm going to say is far enough away from 21 to reject the idea that the real population average is 21. So this is my area of rejection. It's also alpha. 0.05, this is 5% of the graph. Right in here is 5% of the graph, my area of rejection. This is my rule. Any averages in here, I'm going to say, are too extreme, too far away from 21 to reject the null hypothesis. But I'm doing a directional test, so I'm not even going to look in this tail over here. If I found anything out here, I don't care, because I'm only interested in discovering if lawyers are above average, right? And choosing this alpha of 0.05 and putting this entire alpha in this tail creates a critical value of 24.28. So this is the critical value of 24.28. I say to myself, if I'm doing a directional question, I'm only looking in the upper tail, I'm only looking in this one tail to determine if pre-law students are higher than average, then my critical value becomes 24.28, right? The number along this number line on the x-axis cuts off this upper 5%. So this is my area of rejection. I would reject the null if I got a 25. I would reject the null if I got a 25.5 or a 26. I reject the null if I get a 27. But any averages down here, and I'm not going to reject the null hypothesis because they're not in the alpha area, right? Now, what did I actually get? Well, what I actually got was a 23. That was here, right? My actual sample average was 23. See here? My actual X bar is 23. So on my infinite number of samples, where I assume that the real average is 21, because that's the null, 23 would be here. Now and because that doesn't fall into my area of rejection, I say to myself, well, getting a sample average like 23 looks pretty probable. It's pretty close to 21, right? So I'm going to fail to reject the null hypothesis because 23 is not in the area of rejection. See how this value is not in the red area, and 23 is not bigger than this critical value here. Both of those things are true, and they will always have to be true if you're failing to reject the null. If you fail to reject the null hypothesis, your actual X bar, your sample average, is not going to be in the area of rejection. It's not going to be bigger than your critical value, period. So in this case, I am failing to reject the null. Failing to reject the null, and that would mean P is going to be bigger than alpha. And here is then, right in here, this whole area in here becomes my p-value, and as you can see, the p-value completely engulfs alpha. P is bigger than alpha. Anything above 23 is how probable 23 is, right? This whole area is how probable 23 is if the null is true. And so this is bigger than alpha. Fail to reject the null, right? And so all of this is from last time, right? All of this is sort of putting together all of the pieces for a null hypothesis significance test. But now I have to introduce you to a new distribution. So get ready. I'm going to introduce, we've learned all about the null hypothesis sampling distribution. And it's the null hypothesis sampling distribution that we're going to test in the hopes that we find something extreme enough to reject the null. 23 was not extreme enough. 25 would have been. 27 would have been. 29 would have been. But 23 simply isn't. Not extreme enough to reject the null. Fail to reject the null. Retain the null. And you're sad because you're essentially saying that these pre-law students are no different from the general population that has an average of 21. Fail to reject the null. And so we only ever use the null hypothesis sampling distribution to decide, should I reject or fail to reject the null? And in our class, we're actually going to use the critical value approach, right? Where we know that when we set an alpha of 0.05, this created the critical value of 24.28. Anything higher than 24.28, reject the null. Anything less than 24.28, fail to reject the null in a one-tailed directional test, right? But now I'm about to introduce a brand new distribution to you, another sampling distribution of the mean. Are you ready? Whoa. And here it is. Here is two distributions now. Here is that null hypothesis sampling distribution in blue, but then laying right on top of it is called the alternative hypothesis sampling distribution. The alternative. So this is a theoretical, hypothetical sampling distribution of the mean where you assume the alternative hypothesis your awesome research hypothesis, is the accurate one. So instead of being centered on 21, like the null hypothesis is, it is centered on your X bar. 23 was our X bar for this example. So the alternative hypothesis sampling distribution lays right on top of it. Now you could actually draw these as separate distributions on totally separate graphs. And you can do that if you want. So let me draw that for you. You could do it like this. You could say that the null hypothesis is centered on 21, with one standard error way being 23, right? And then you could draw another sampling distribution down here. This one centered on 23, and that would be the alternative hypothesis sampling distribution, right? This one is centered on 21 because it's the null hypothesis. This one is centered on 23 because it's the alternative hypothesis sampling distribution. But when you lay these, and they both have the same amount of standard error, because standard error is still going to be 6 over the square root of n. They're both normally distributed, right? They're both going to have, they both are going to be based on samples with 9 people in them. So they're going to be identical, except for the fact that the null hypothesis says the average will be 21. And the alternative awesome research hypothesis says that the real average is going to be closer to 23. In the population, 23 is meaningful. So you simply center the alternative hypothesis sampling distribution, the research hypothesis sampling distribution, on 23. But then you lay them on top of each other like this. And so now what I've done here is I've gotten rid of all that shading in. So you can really see this new red distribution called the alternative hypothesis sampling distribution laid right on top of our blue null hypothesis sampling distributions. And these two sampling distributions represent our our competing hypotheses, right? Here we've got the blue one. Here we've got the blue one centered on 2021. And here we've got this new red one centered on 23, because that was what the X bar was. And so if the null is true, 23 is just a random sampling error from a population that has an average of 21. But if the alternative is true, 23 is meaningful. 23 is meaningful. And so we lay them on top of each other. But then so we've got these two competing hypotheses. Now watch. This black line here is still our critical value. And this area here, which I have not shaded in for you, is still alpha. But alpha only lives on the blue distribution. So here is alpha. Here's our critical value of 24.28. And here's the alpha. Here's the area of rejection on the null hypothesis sampling distribution, right? And that we've already thought about. If we find it's null hypothesis significance testing, so we're going to use this blue distribution, this null hypothesis sampling distribution, to decide whether or not to reject the null. If I find a 25 or a 27 or a 24.29, anything in the area of rejection, anything bigger than this black line, this critical value of 24.28, I'm going to reject the null. Anything over here, and I failed to reject the null. And so this area is in fact called alpha on the blue distribution. But what if the alternative is true? What if the alternative is true? All right. Well, this area, this left-hand side of the alternative distribution is called beta. And if the alternative is true, this area here is the probability of not rejecting the null and being wrong. The alternative is actually true, and if we find a 23 or a 22 or whatever, this is going to be the proportion of times we're going to sort of fail to reject the null when we should have. This area here is called beta in pink. This area here is called power. This area here is called power. And this is everything over here, we're going to reject the null hypothesis, which is what we want to do. We're rejecting the blue distribution so we can go with the red distribution. And if we get a 25, a 27, a 29, we'll in fact do that. We'll be rejecting the null and we'll be happy because we want to do that. We want to go with the alternative. And so anything over here, we're going to be rejecting the null and being happy and being, yay, happy, 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 right? And so we call this area power. So the null hypothesis is the assumption that the null is true. Anything over here, we're going to reject it anyway, and that's alpha. Anything over here, we're going to fail to reject it. That doesn't get a special name because, well, we're failing to reject the null. We're not rejecting the null, and we're living on the null distribution. But when we select an alpha and we select a critical value of 24.28, that not only cuts up the null hypothesis sampling distribution into alpha and then not alpha, but it also splits up the alternative hypothesis sampling distribution into failing to reject the null, so sad, I wanted to go with the alternative, and I'm so sad, I can't, and power, which is rejecting the null, being happy because you're going with the alternative, and that's called power. Anything over here is like a powerful result. Yay, we're going with the alternative, and the alternative is actually correct because now this distribution assumes that it is. So this area is called power, right? And so for now, what I want you to do is just memorize these areas. This little teeny area here, this little teeny area here is called alpha. The left-hand side of the alternative hypothesis sampling distribution is called beta. It's where we're failing to reject the null, but the alternative is actually correct. And this area here to the right on the alternative hypothesis sampling distribution is called power, where you're rejecting the null and you're assuming the alternative is true, so you're right. Just memorize those for now. So the first way I want you to understand these three important concepts of alpha, beta, and power is just places on two sampling distributions that have competing assumptions. There's the null hypothesis assumption, that's the blue distribution, centered on 21. There's the alternative hypothesis assumption that 23 is the real average in the population, and so the red distribution is centered on 23. And then once you pick a rule, an alpha, that determines a critical value. In this case, that critical value is 24.28. Once you've done that one critical value of 24.28, you've got on the null hypothesis assumption distribution, the one in blue, you've got anything to the right on the blue one is alpha, anything to the left is 1 minus alpha, because the entire distribution is 1, right? We're dealing in probabilities here, we're dealing in proportions, the entire graph is 1, and this little area here is alpha on the blue distribution only. And then everything left over is going to be 1 minus alpha, or 0.95 in this case. But that one critical value of 24.28 also carves up the alternative hypothesis sampling distribution. That sampling distribution that you create under the other assumption that 23 is meaningfully different from 21. And so these lawyers need their own sampling distribution. And this one critical value of 24.28 carves up this other distribution into two as well. Anything to the left is beta, where you're not rejecting the null hypothesis and you're sad. And anything to the right is power, where you are rejecting the null hypothesis and you're happy, right? And so this is the first way I want you to understand these sort of phrases, alpha, beta, and power, and be able to label them on this graph. I see that in your future. But there's actually other ways to understand alpha, beta, and power. And they actually flow conceptually from these graphs. And it's like this. Alpha is the probability of rejecting the null even if the null is true. But I thought alpha was our rule. I thought it was that little area on the graph. It is. But determining that little teeny area on the graph, that little alpha area, that area of rejection, also creates this conceptual understanding. Alpha, whatever you choose it to be, usually it's 0.05, is also the probability of seeing a weird sample just due to chance. It is the probability of rejecting the null even if the null is true. And if you think about it, the null is this super boring thing. It's saying that the averages are not different. And they very well could be. The null could be true, right? This null hypothesis sampling distribution could be the right one. But if you find anything in alpha, you're going to reject the null anyway. So alpha is, in fact, in addition to being the area of rejection, in addition to being that rule that we create, anything in the extreme 5%, anything in the extreme probability or proportion of 0.05, anything in there we reject the null, but if the null is true, we're making a mistake. So alpha is the probability that even if the null is true, we're going to reject it. And so that's another way to understand alpha. It's the probability of making this kind of error, where even if the null is true, we're going to reject it anyway. Even if these groups are not different from one another, if I find anything extreme, I'm going to reject the null anyway. And so 5% becomes what's called our baseline, right? Our baseline for making this mistake. There's a 5% chance that I'm going to reject the null even if the null is true. So that's one way to be wrong. Another way to understand beta, yes, beta is this area on this curve, right? Beta is this whole pink area here, right? If the alternative is true, this is the probability that we're not going to go with the alternative, because any averages over here, we're going to fail to reject the null. And if the alternative is right, that's a huge bummer. So yes, beta is this area here, but beta is also the probability of rejecting the alternative even if the alternative is true. Beta is the probability that you're going to fail to reject the null, because anything over here, we're going to fail to reject the null, right? Beta is also the probability of failing to reject the null, but we should have. We failed to reject the null, but in reality, the alternative is true, and we should have rejected the null, but we didn't. So beta is the probability of doing that. And something important I want to point out now is you're never going to know. You're never going to know for sure. Is 23, from my example with lawyers, actually just sampling error? Is the null true? Is 23 real and meaningfully different in the population? Is this 23, does this represent actual meaningful differences between pre-law students and the general population? We don't never going to know for sure. So we have to play this probability game where we say, let's assume the null is actually the true one and figure out how weird my sample looks under that assumption. If my sample looks too weird, then I'm going to reject the null. Well, how weird is weird enough? Weird enough to be in the extreme 5%, in the area we're going to call alpha, right? So then, but then alpha is also the probability, even if the null is true, that we're going to reject it anyway. And it's usually, and we get to decide what it is. We get to decide what alpha is, 0.05 usually. But beta is the probability of rejecting the alternative, which means we're failing to reject the null. It's a very weird idea. If we fail to reject the null, we're sad. We're retaining the null because we don't get to go with our alternative. Sad. But if the alternative was actually true in the population, that sucks, and we've made a mistake. And the probability of that is beta. The probability of the alternative being true, but going with the null instead. Failing to reject the null, but in reality, the alternative was the one to go with. And you don't know what it is. You don't know what, you're never going to know for sure, but you know the probabilities. You know the probabilities of rejecting the null, even if the null is true. That's alpha. You know the probability of failing to reject the null when you should have. Beta. And that's the idea. These are the two, these theoretically are the probabilities of making a mistake. The probabilities of, and there's only two mistakes you can make, right? You can either reject the null and be wrong. The probability of that is alpha. Or you can fail to reject the null and be wrong. And the probability of that is beta. And if no matter what decision you make, you might be making a mistake, right? If you choose to reject the null, there's some probability that's a mistake. And the null is actually true. The probability of that is alpha. You get to pick it, usually 0.05. But if you choose to fail to reject the null, if you retain the null, that could also be a mistake, because the null could actually be false. The probability of that is beta. But no matter what decision you make, you could be making a correct decision. You could in fact be making a correct decision. And power then is the probability of, if you reject the null, you're making the right decision because the null is in fact false. The alternative is the one you should have gone with. And so it is the probability of going with the alternative, and in fact the alternative is true. It's the probability of rejecting a false null. Whoa. Remember, the null is what you want to reject. And so power is the probability of making this kind of correct decision, right? You're rejecting the null, and the null is in fact false, rejecting this terrible, horrible null hypothesis, and hooray, the null is in fact something you should have rejected. It's false. Power is the probability of doing that. Power is the probability of finding a difference between your groups and that being the right decision, right? And because power and beta are two halves of the same graph, let me show you this graph again, because this is power over here in sort of teal greenish, and this is beta. This is the two halves, they're not equal halves, but these are the two halves of the alternative hypothesis sampling distribution. And so beta is 1 minus power, and power is 1 minus beta, because the entire alternative hypothesis sampling distribution is, again, 1, because this is the whole thing is 1, and then you carve it up, right? So power is also known as 1 minus beta sometimes, right? And then this is alpha, and this is the Greek symbol for alpha, and this is the Greek symbol for beta, right? This is just the Greek letter of beta. And so power is the probability of rejecting the null and being right. And then 1 minus alpha, doesn't get a special name, is the other way that you could be right. And it doesn't get a special name because it's the most boring way to be right. You have retained the null, you failed to reject the null, and you're now assuming that the null is in fact true. The most boring way to be right. And so that's this whole area here on the null hypothesis sampling distribution. Right, here's alpha. This whole thing is 1. 1 minus alpha is this area here. And so think about power and 1 minus alpha as the probability you're making a correct decision no matter what decision that you make, right? Here's power. It's the probability of rejecting the null and being right, going with the alternative, and that being a good decision if you choose to reject the null and go with the awesome alternative, right? 1 minus alpha is the probability of making a correct decision if you are going to stay with the null, fail to reject the null, and not go with the alternative, 1 minus alpha. So these are the probabilities of making a mistake no matter what decision you make. And these are the probabilities of making a correct decision no matter what decision that you make, right? And so let's say you're going to reject the null hypothesis. You're either making a mistake and the probability is alpha, or you are making the right decision and the probability of that is power. But let's say you are failing to reject the null. That could be a mistake. The probability of that is beta. Or that could be a correct decision, and the probability of that is 1 minus alpha, right? And so not only are alpha, beta, and power areas on these two distributions, there are also these formal definitions that I need you to know, right? Alpha is the probability of rejecting the null, even if the null is true. Beta is the probability of rejecting the alternative, even if the alternative is true. Put another way, you could say beta is the probability of retaining the null, failing to reject the null, even if the null is false. Crap. This car is a lemon. This hypothesis is a lemon, but I'm failing to reject it. I'm keeping that. Power is is not only an area on this graph, it's this little teal area here. Power is also the probability of rejecting the null hypothesis, going with the alternative, and being right. 1 minus alpha is in fact an area on this graph, but it is also the probability of failing to reject the null and being right because the null is true. Both of those things are true. Now, I keep talking about being right and being wrong, right? And we actually get, and here are the probabilities of these two errors. Alpha is the probability of rejecting the null, and whoops, the null is true. Beta is the probability of rejecting the alternative, and whoops, the alternative is true. We actually give these two possible mistakes special names. We call them type 1 and type 2 error. Now, if you reject the null, and the null is in fact true, the probability of that is alpha, and you're making what's called a type 1 error. And so the probability of a type 1 error is alpha. And so alpha is also often called the type 1 error rate. How many times you will make a type 1 error on your null hypothesis sampling distribution of an infinite number of averages, right? But the bottom line is, we talked about how alpha is the probability of rejecting the null, even if the null is true. Well, that's a mistake. If you reject the null and the null is in fact true, that would be a mistake. And we call that mistake a type 1 error. Now, you might not be making an error, but if you are, it's called a type 1 error. Now, again, you're never going to know, but you do know the probability of a type 1 error. It's alpha. The probability that you're going to reject the null, even if the null is true, is whatever you decide it to be, 0.05 usually. Whatever your alpha is the probability that you're making a type 1 error, rejecting the null, even if the null is true. But what about this other error? What if you decide not to reject the null? What if you fail to reject the null? Well, if that happens to be a mistake, that is a type 2 error, right? Where you don't reject the null hypothesis, you're not rejecting it. You're failing to reject it. And you're failing to reject this hypothesis called the null. And in fact, the null hypothesis was a lemon. The null hypothesis was false. You don't know that, but in reality, that was what was true. So if you don't reject the null, you're keeping the null, like a terrible car, like a lemon. You're keeping the null. And in reality, this null hypothesis is a lemon. You should have rejected it, but you didn't. Well, that kind of mistake is called a type 2 error. And the probability of a type 2 error is beta, whatever beta is. Now, are you ever going to know for sure, no matter what decision you make, whether or not you're making a correct decision or whether or not you're making an error? Nope, you're never going to know. But you do know the probabilities of each. The probability of a type 1 error, if you decide to reject the null, is whatever you set alpha at. If you set alpha of 0.05, you're saying, well, even if the null is true, 5% of the time I'm going to reject the null anyway. So my type 1 error rate is 0.05, whatever alpha is. But if I fail to reject the null hypothesis, I don't know if I'm for sure making a mistake, but I know the probability of making this other type of mistake called the type 2 error, and that probability is beta, right? You're never going to know for sure, but you can determine the probabilities of each. Alpha is the probability of a type 1 error if you choose to reject the null. Beta is the probability of a type 2 error if you choose to not reject the null. Keep that null around like a terrible lemon car. Now, let's talk about some things that can impact these probabilities. Because what you want is for the probabilities of the errors to be low. You don't want to make mistakes, right? Your goal is to not make mistakes. You want alpha to be as small as you can make it, but without being so small that you're never going to reject the null. So usually you just set it at 0.05. You say, I'm willing to accept a 5% error rate. I'm willing to reject the null, even if the null is true, 5% of the time, which is why it's normally set at 0.05. That number, 0.05, just feels good to researchers. But power, so alpha doesn't change except by what you decide it's going to be. But power and beta, on the other hand, can and are affected by aspects of your study. Now, beta is the probability of making that type 2 error, so you want it to be small. Power is the probability of making that correct decision when you are rejecting the null, which is what you want to do. Power is the probability of making that correct decision when you reject the null, right? And so you want this probability to be big. You want beta to be small, and you want power to be big, right? And so here are some things that can affect power and beta. Sample size. The greater your sample size, right? Like let's say instead of 9 people, I grabbed 16 people. Instead of 16 people, I grabbed 25, right? Increasing your sample size is going to make power bigger and beta smaller. So that's something that's under the control of the researcher, which is one of the reasons why it's a good idea to grab a lot of people if you can as the researcher, because this is going to make power bigger and beta smaller, which is what you want. The probability of that type 2 error gets smaller, And then the probability of making a correct decision that we call power gets bigger. Another thing that affects power and beta is your effect size, the difference between your averages. Now, in my example with the lawyers, the difference between my averages was 21 versus 23. That was the effect size, right? The bigger the difference between the averages, the greater power is and the smaller beta is. Now, you can't manipulate this directly, but that is something that will impact power, right? The bigger the effect, the smaller beta will be, the bigger power will be, which is what you want. The standard deviation also matters. The smaller the standard deviation is, right, the smaller variability is, the smaller standard error will be, right? Sigma over the square root of n, right? Sigma over the square root of n, the smaller this number is, right, the smaller standard error will be, and so that's going to make power bigger, beta smaller. Now, standard error is going to be what it is, right? The standard deviation for the population is what it is. But in fact, populations that have smaller variability, right, are going to have higher power, lower beta. But also the alpha you choose. The alpha that you choose can also impact power and beta. Now, I wouldn't recommend making your alpha bigger on purpose, because if you increase alpha, you're increasing the likelihood of that type 1 error, right? So that's not a good idea. But in fact, if you make a bigger alpha, this will make power bigger and beta smaller. Bigger alpha is going to make power bigger and beta smaller, because if it's a bigger alpha, you're moving that critical value, which then allows power to be bigger and beta smaller. But that comes at a cost. You're going to have smaller beta error, but more alpha error. So that's not a good idea. And also the difference between a one and a two-tailed test. A one-tailed test is going to have bigger power, smaller beta, but that's not a good idea to do one, right? Just because a one-tailed test is going to have bigger power and smaller beta, that's not a good reason to do one, because that means you're not allowed to look in that other tail. But it is in fact true that a one-tailed test is more powerful and has smaller beta. So if you can safely theoretically argue that only looking in one tail, only looking in one direction for the effect is reasonable, well, then maybe you might want to do a one-tailed test. Most behavioral scientists don't do them, but they are somewhat more common in the medical sciences, just so you know. A one-tailed test is in fact more powerful than a two-tailed test. And more power means less beta. All right, so I just want to go over this one more time, alpha, beta, and power, and watch how things like sample size can affect alpha, beta, and power to sort of allow you to sort of get your mind wrapped around these concepts, right? And again, these are concepts you have to sit with for a little bit. Try to get your noodle wrapped around them. And so let's take our example from before with the pre-law students, right? Do pre-law students score higher on the ACT than students in general? I've got a sample of 9 pre-law students that had an X bar of 23, and then I'm going to compare that to a null hypothesis population that itself has an average of 21 and a standard deviation of 6, right? So I've got an effect size, so I've got a sample size of 9, which matters because that's how I'm going to get my standard error. I've got an effect size of 2. The difference between 21 and 23 is in fact 2. My alpha is set at 0.05, and this is a one-tailed test. So all of alpha is going to go in one tail only, right? One tail only, and I'm only going to have one critical value. And so what is my standard error? Well, sigma over the square root of my sample size, so 9. So 6 over the square root of 9. Square root of 9 is 3. So 6 over 3. And so standard error is 2. And that's actually what I have down here, see? So, and I've got my null and alternative hypotheses, these two sampling distributions on the same graph, so we can see and visualize alpha, beta, and power, right? And this is and so then the critical value, and this is the same distribution that I showed you before. Choosing alpha is right here, this dark purple area here. And then choosing an alpha on the null hypothesis sampling distribution creates a critical value of 24.28. So this line that was created when I chose an alpha of 0.05 only in one tail, created a critical value of 24.28, which also then carved up the alternative hypothesis sampling distribution into power, the probability of rejecting the null hypothesis and being right, finding that these groups are different, yay, and you're in fact correct. This is power, that's what you want, and this is beta, the probability of making that oopsie mistake. And as you can see in this example, the probability of beta is pretty darn big. The probability of failing to reject the null and being wrong is pretty darn big, right? You can sort of see that. And that's because sample size is small. With only 9 people, the standard error is big at 2, right? The standard error is based on not only sigma, but also the sample size. And so here you can see that there's a lot of overlap between these two graphs because standard error is pretty big. There's a standard error of 2. But let's see what happens when we change our sample size. The only thing that changes now is sample size. We're assuming everything else is the same. We still got an average of 23, but now this average in our sample of 23 isn't based on 9 people, it's based on 36. So now my theoretical, hypothetical sampling distributions of the mean don't have 9 people in each of them, they have 36. And so now each sample average is a little more accurate because it's based on 36 people, and so standard error is going to be smaller because each sample average is going to be more accurate. And so now let's figure out what my standard error is. Nothing else has changed but my sample size. But now 23 is, that sample average of 23 is not based on 9 people, it's based on 36 people. So let's see what that does. We get 6 over the square root of, 36. And so now the square root of 36 is 6. And so now standard error is 1. And so now notice my null hypothesis sampling distribution, it's still normal, but now 1 standard error away is 22, not 23. 2 standard errors away is 23. So the standard error has changed and gotten smaller because my sample size got larger, which is exactly what the central limit theorem said would happen. But now this is going to change my critical value. Notice my critical value is different now because now alpha doesn't change, it's still 0.05, right? But now alpha is here. And so now my critical value is different. My alpha is still 0.05, but because standard error is smaller, my critical value is different. Now my critical value is right around 23 because standard error got smaller. Alpha is still 0.05, but because standard error got smaller, because sample size got larger, I now have a critical value of something close to 23. And so now let's look to see what that much smaller critical value, what effect that has on alpha, what effect that has on beta and power. Alpha is still 0.05. This is still 5% of the graph, right? Except now 5% has very different critical value because standard error is smaller. So let's watch what happens to beta and power. Now, this is alpha. This whole blue area here is now alpha. And so now this is my critical value. And so notice that more people made power a whole lot bigger because standard error was smaller. And beta was a whole lot smaller because of the smaller standard error. Increasing the sample size without monkeying with alpha at all, alpha is still 0.05 right here. But now power is a whole lot bigger and beta is a whole lot smaller because standard error is smaller. And that's what you want. You want power to be big. You want to, which is why researchers often get a whole lot of people, because a whole lot of people are going to make your sample average, whatever it is, be based on a much more accurate average, right? An average based on 36 people is going to be a whole lot more accurate than an average based on 9 people. So when you create your theoretical hypothetical sampling distribution of the mean, it's going to have small standard error. So you get to make your alpha at 0.05, while at the same time, and again, alpha is your type 1 error rate. It's your area of rejection. You get to set that at 0.05, and then because you have a large number of people that your X bar is based on, you can make your standard error as small as possible so that your power is big and your beta is small, which is what you want, because power represents the probability of finding something statistically significant and being right. Finding some statistically significant difference between the average and being right, which is what you want, right? And so power is the probability of going with the alternative if the alternative is true, and you want that probability to be big because most researchers think their alternative is true, so they want the probability of going with that alternative to be as big as possible, right? You want to reject the null, right? So putting that another way, power is the probability of rejecting the null and being right. And that's what you want to do. Reject that bad, lame, lemon null and be right. So power is the probability of finding some interesting relationship, some difference between the averages that really exists out there, right? Power is that probability, and you want that to be big. And one of the ways that researchers can do that is just make sure their X bars are based on a whole lot of people so that their null hypothesis sampling distributions have small standard error. Because then when you choose your alpha, which then determines the critical value, beta will be small and power will be big, which is what you want. Now again, if any of these ideas are confusing, feel free to post in the Q&A forum, or if you want a more one-on-one interaction, come to my office hours and we can talk about these things, and I'll draw you lots of pictures and I'll go through lots of different examples if that's what you need. But this is our last topic before the second exam. And so do please look at that study guide for the second exam. Make sure you can answer all the questions on that study guide, and then come to me if there's anything on the study guide that you're confused by. And come to me if you have any questions at all. Post in the Q&A forum, email me, or come find me in person in my office. I'm always happy to see you. All right, see you after the next exam. Have a good one.